LLaVA, which stands for Large Language and Vision Assistant, is a groundbreaking multimodal model that integrates visual and language understanding capabilities. Developed as an open-source project, LLaVA represents a significant advancement in artificial intelligence, particularly in bridging the gap between text-only models and those that can process both images and text simultaneously. This model is designed to understand and generate content based on visual inputs and language instructions, making it a versatile tool for various applications, including visual question answering, image captioning, and more. The community has experienced a remarkable increase in public multimodal data, specifically image-text pairs, as seen in resources like CC and LION. However, the availability of multimodal instruction following data remains relatively scarce. This limitation is largely due to the time-intensive nature of creating such data, compounded by the challenges of defining the process when relying on human crowdsourcing. Drawing inspiration from the recent achievements of GPT models in text annotation tasks, ChatGPT and GPT-4 are utilized to collect multimodal instruction following data, capitalizing on the extensive existing image pair datasets. It transforms a basic image-text pair into a more robust instruction following format. 3 distinct types of instruction following data, starting with a few manually crafted examples to guide the in-context learning process with GPT-4. Conversations, simulated dialogues where the assistant answers questions related to the image, covering aspects like object types, counts, actions, and spatial relationships. Detailed descriptions, aimed at providing comprehensive visual summaries, where GPT-4 generates descriptions based on randomly selected questions. Complex reasoning, questions that necessitate rigorous reasoning and logical steps to derive answers from the visual content. In total, we amassed 158K unique language image instruction following samples, categorized into 58K for conversations, 23K for detailed descriptions, and 77K for complex reasoning. Our initial experiments revealed that GPT-4 consistently yields higher quality instruction following data, particularly in spatial reasoning tasks. LLaVA employs a unique architecture that combines a vision encoder with a large language model. Specifically, it utilizes the contrastive language image pre-training model as its vision encoder, which is adept at understanding images in conjunction with textual descriptions. The language model component is based on Vicuna, which is designed to generate coherent and contextually relevant language responses. The integration of these two components allows LLaVA to process and respond to multimodal inputs effectively. The architecture includes a linear projection layer that serves as a bridge between the visual features extracted by the clip model and the embedding space of the language model. This projection layer transforms visual features into visual tokens, aligning them with the language model's word embeddings, thus facilitating seamless multimodal interactions. Stage 1: Pre-training for feature alignment. In the initial stage of training the LLaVA model, a subset of the CC3M dataset is filtered down to 595,000 image-text pairs to ensure a balance between comprehensive concept coverage and training efficiency. The details of this filtering process can be found in the appendix. These selected pairs are transformed into instruction following data using a straightforward expansion method. Each data sample is treated as a single-turn conversation, where for a given image and a question is randomly chosen. This question serves as a language instruction prompting the model to provide a brief description of the image. The correct answer corresponds to the original caption of the image. During this phase, both the visual encoder and the large language model, LLM, weights remain unchanged, while only the projection matrix W is trainable. The objective is to maximize the likelihood of the model's predictions, effectively aligning the image features with the pre-trained word embeddings of the LLM. This stage can be viewed as training a visual tokenizer that is compatible with the frozen LLM. Stage 2: Fine-tuning end-to-end. In the second stage, the training process shifts to fine-tuning the model in an end-to-end manner. The weights of the visual encoder continue to be kept frozen, but both the projection layer and the LLM weights are updated. Thus, the trainable parameters now include both the projection matrix W and the LLM parameters. This approach allows for a more integrated training process, enhancing the model's ability to understand and generate responses based on visual inputs. LLaVA is a cutting-edge model in the machine learning field that focuses on multimodal instruction following tasks. By leveraging large language models like GPT-4, LLaVA enhances the generation of instruction following data from existing image-text pairs. It employs symbolic representations, such as captions and bounding boxes, to encode visual content, facilitating better interaction between text and images. LLaVA produces diverse instruction-following samples, including conversations, detailed descriptions, and complex reasoning tasks. This innovative approach significantly improves the quality of multimodal data, enabling advanced applications in areas such as computer vision, natural language processing, and human-computer interaction.